Today I want to show you how to plot the Bode plots and see the frequency response of your circuit using your oscilloscope. So these Bode plots gives you the frequency response and the phase graph of your circuit. In total, the thing that is really important for us in circuit design is the bandwidth. And these frequencies are cut-off frequency. After this frequency, we don't have the amount of the gain that we expected from our circuit. So this is gonna call our bandwidth. And in this place, the gain that we had will be attenuated for 3 dB, meaning that this dB means decibels. So it means that your gain is about 0.7 of your expected gain. So after this, they say that this is a stop band and here is the pass band. And in the cutoff frequency of the 3 dB, we are gonna have a 45-degree phase shift. So for example, in my circuit that I showed you in my previous videos, the gain is about 1000. So V out to in is about 1000 and the logarithm of 1000 is 3. So 20 times 3 gives us 60 dB. So instead of 0 dB, we're going to have 6 dB. And if we look at the 3 dB drop, which is going to be at 57, it's going to give us the cutoff frequency, meaning that for any frequency after that, we're not going to see our expected gain. So this is the oscilloscope. Whenever we want to get the Bode plot from the oscilloscope, we connected this generator output probe to the input of the circuit, and we put this oscilloscope probe same as here to see it, and this is going to be the output of our circuit. So this generator is going to sweep around the different frequencies for us and generate them. It's going to give it to your circuit and get out the output. So after putting this, we go to the analyze. For the feature, we choose the frequency, and we have the settings in here. So if I go to the setup, this is the way that we can generate it. As I said, the gen part is going to generate the wave. It goes inside our circuit. Probe 1 is going to see it, so it's going to be connected to V in, and probe 2 is the output, so it's going to be connected to the V output. We can decide about the minimum frequency and maximum frequency, so let's keep it for 10 Hertz and 1 megahertz or 100k hertz. This is gonna be the amplitude. I want to show it for the 20 millivolt peak to peak for now, and these are the other things that you can do. After that, you click the back and run it. While it is running, you see the yellow is the input that is your oscilloscope is giving to your circuit, and the output is the green one. So the idea is that for different frequencies, it generates something that give it to your circuit and get out the output and generate the Bode plot. As you see, the Bode plot is getting generated. The blue one is for the gain and the frequency, and the red one is for the phase. And as you see, it's started from 60 dB because the gain of my 2-stage amplifier shown in my previous picture is this much. So this is the final picture. So as you see, this amplifier without any extra capacitors added to that is working like a low-pass filter actually. And the reason is that all these elements, especially these op-amp, has some hidden capacitors inside. So if I look at the gain for the frequency, which is 60, if I put it on the move, and from here, which is about around 60, let's say 57, if we reduce it for 3 dB, which is gonna be around 54, something around here, 54, 55, this is gonna be the 3 dB bandwidth that I showed you in theory. As you see, the phase shift is negative 45, around 45, and this is amount of that. And it's happening at 10 kilohertz. So it means that 10 kilohertz is the stop band, is the cutoff frequency of this amplifier. If we give an input to this amplifier, which is frequency is more than 10 kilohertz, we cannot get that expected gain. After this one, the gain will be attenuated. That's the reason we say that these amplifiers are not useful for high frequency analysis.